Improper integrals. We have the integral from 0 to 1 of 1 over x dx. It's a good thing to try to do this one. If you did it, you would say the ln of absolute value of x, and you would evaluate from 0 to 1, and you could find the ln of 1. That would be easy. That's 0. And what's the ln of 0? It's undefined. What's the problem with this? Especially based on what we've done and what our definition that our book uses. The problem is 1 over x is not defined on the closed interval from 0 to 1, which is what we normally deal with. Deal with for definite integrals. We also had, if we had a finite number of discontinuities. Now this is continuous. It's a continuous graph on its domain, but it's not continuous on the closed interval from 0 to 1. So what I'd encourage you to do is think, do you have any ideas on how you could do this? You could pause it and then come back. Assuming you've done that, number one, what we're going to try to do is integrate on a closed interval inside the non-closed interval. So in other words, we are going to make this have a closed interval, and then we'll expand it out so we can get the interval that we're looking for in the first place. How do we expand that out? What is that idea? That is, take the limit as the closed interval becomes the non-closed interval. And that's the basic idea. So if we take a look at I'll give a little thing here. It says a to c, for example. And so this function, let's say I'm going to integrate from a to c of f of x dx. What do I want to do? I'm going to stop it before there, and I'll call that b. So now I do have a closed interval from a to b. So I'll start off with the closed interval from a to b of f of x dx. But then I got to take that limit as b goes to c. So b is going towards c. So limit as b goes towards c from what side here? In this case, we're coming in from the left side. It could be coming in from the right side. So let's go back to number 1, and we look at 0 to 1 of 1 over x dx. If I just assume we know what that graph looks like. So this is not closed at the 0 part. So we will say the limit as b goes towards 0 from what side? We're coming in from the positive side of the integral from b to 1 of 1 over x dx. So we'll have the limit as b goes to 0 from the right side of the ln of the absolute value of x evaluated from 1 to b. The limit as b goes to 0 from the right side of the ln of 1 minus the ln of b. Now the ln of 1 is 0, so we're going to be going to minus the ln of b as b goes towards 0. Recall the graph of ln looks like this. And so as b goes to 0 from the right side, that's going to negative infinity. So this thing is going to go to positive infinity because it's negative of negative infinity. Let's take a look at just a couple other examples of improper integrals. You could say something like this: 0 to 2 of x plus 1 over x plus 2 dx. We dealt with this kind of problem before, but we dealt with it using area. Another example might be 0 to infinity. If you're going to infinity, that's definitely not a closed interval. Of 0 to infinity of e to the negative x dx. The limit, if it exists or not, is the improper integral of the function over the non-closed interval. So, regardless if it exists or not, whatever we get from that limit is what that improper integral is going to be. So some questions to ask about this. Does the limit exist? If yes, the limit and the improper integral converges. If no, the limit and the improper integral diverges. Now we have some tables that are in your textbook, and I will show them to you now before I start doing some examples. They are on pages 434 and then 436. So integrals with infinite limits of integration are improper integrals. So we're talking about if we have infinity in there. If we go a to infinity, we'll find the limit as b goes to infinity from a to b. And similarly, if you're going to go on the other side, negative infinity to b, well, you're going to say the limit as a goes to negative infinity in this case, and then go a to b. It really doesn't matter what letter we use there. Just to stay consistent, the book's going to go the a and then the b, so they'll use a for the lower and b for the upper, but it doesn't matter. If you have from negative infinity to infinity, you would have to break it up into two separate integrals and find the limit, then going to negative infinity as in number 2, and then go positive infinity as in number 1. Here's another one. And this one's dealing with basically like the example I just did from 0 to 1 of 1 over x. If it's not continuous at, or it's not at a closed interval a, then we're going to say the limit as c goes to a from the right side. If we go into b where it's not closed, then we're going to go c goes to b from the left side. And then if you have something in the middle, you're going to have to break it up into two integrals as well. Now let's take a look and start doing some other examples. We'll have number 2, the integral from 1 to infinity of 1 over x dx. So we can see here that's an improper integral since it has infinity. That's clear to. We have. Let me leave a little room so I can write my limit. We're going to go from 1 to b of 1 over x dx, and then we'll have the limit as b going towards infinity. So once we do this, we'll just write limit as b going to infinity of ln of absolute value of x evaluated from 1 to b, which equals the limit as b goes towards infinity of ln of b minus the ln of 1. And recall our graph that we did on the previous problem, that the ln is going to, as that b goes to infinity, the ln goes to infinity, so this thing diverges. Let's do a couple more examples. Number 3. The integral from negative infinity to 0 of 1 over the cube root of x minus 1 dx. So where is the problem here? We can see that if we plug in 1, that's not going to work. But if we look at our interval here from negative infinity to 0, 1 is not even in that interval, so we don't need to worry about the 1. So the only problem we have here is for the negative infinity. So let's write the limit as b goes towards negative infinity. I tend to just use b. Of b to 0 of, I'm going to rewrite that integrand as x minus 1 to the negative 1/3 dx. So we can copy over limit as b goes to negative infinity, find the antiderivative of x minus 1 to the negative 1/3. So that would be x minus 1 to the 2/3 divided by 2/3 or multiplied by 3/2 evaluated from b to 0. Plug in our limits. B goes to negative infinity, and then that would be what? So if I plugged in 0, that would give me 1, minus if I plugged in b, that's going to give me, let me just pull out the 3/2 there so I don't need to worry about that. So plug in b, I'll have b minus 1 to the 2/3. So now what do we have here? We'll have 3/2, 1. As b goes to infinity, what's b minus 1 squared and then cube root? I should say b is going to negative infinity. Since we're squaring that, it's going to make it positive infinity. And we're going to, let's see, we got negative infinity, so that's going to be negative infinity as our answer, and this diverges. Number 4. The integral from 0 to 3 of, and I'll take a look at that same problem we just had. So this time we have an infinite discontinuity at x equals 1. So if we're looking at our interval, we have this closed interval from 0 to 3, but at 1 there's a problem. So that means we're going to have to set this up in 2 limits. We will have 0 to b of x minus 1 to the negative 1/3 dx. And so I'll have the limit as b goes towards 1. From what side are we coming in? We're going to come in from the left side. And then I'll have, it'll be added to, we can't use b for this one, so we'll use c. C to 3, and we'll come limit as c goes to 1. This time we're coming in from the right side of x minus 1 to the negative 1/3 dx. Now, in order for this original problem, the improper integral, to converge, both of these limits must converge. So if one of them doesn't converge, we can stop there and say the whole thing diverges. Let's see what we get. We have the limit as b goes to 1 from the left side of, we've already done this integral, x minus 1 to the 2/3 going from 0 to b. So we'll have 3/2. I'm just going to pull the 3/2 out this time. B going to 1 from the left side of b minus 1 to the 2/3 minus 1 plug in to see if we can. In this case we can. We'll have 3 halves, 0 minus 1, so that's going to give us negative 3 halves. So the first part converges. Now let's take a look at the next part. We'll have limit as c goes to 1 from the right side of 3 halves x minus 1 to the 2/3 going from 0 to 3. And then we can take that 3 halves out. Limit as c goes to 1 from the positive side. Plug in a 3. We'll have 3 minus 1, which will be 2 to the 2/3 minus c minus 1 to the 2/3. When we evaluate it, limit as x or c goes to 1 from the right side, this is going to go to 0, so we'll be left with 3 halves times 2 to the 2/3. This also converges. So what is our answer? 0 to 3 of 1 over cube root of x minus 1 dx equals the sum of those two things, negative 3 halves plus 3 halves times the 2 to the 2/3. So this thing converges, and it converges exactly to that number. Let's look at a couple more. Number 5. The integral from negative 3 to 0 of x over square root 9 minus x squared dx. So what's the problem here? First, the problem is if we plug in this negative 3, we're going to have 0 on the bottom, and that's bad. So we can't have that. So we will end up taking this and saying, in other words, it's not a closed interval. The limit as b goes to negative 3 of b to 0 of x over square root 9 minus x squared dx. So how do we go about doing this? We could do a substitution here. Let u equal 9 minus x squared, so du is negative 2x dx. We'll need to change our limits as well. U of 0 will be 9, and u of b will be 9 minus b squared. So this becomes the limit as b goes to negative 3 of 9 minus b squared to 9. And so x dx will, and I'm going to move the negative 2 to the other side, that will be negative 1/2 du over the square root of u. Let's pull that negative 1/2 out. So negative 1/2 times the limit as b goes to negative 3. Oh, I didn't put what side I'm coming in at. So this would have to be on the right side. Since my interval is negative 3 to 0, I'm coming in from the right side. What's the antiderivative of u to the negative 1/2? That would be u to the positive 1/2 times 2 over 1. And we will evaluate from 9 minus b squared to 9. So the 2 and the negative 1/2 will reduce to just be left with negative. B goes to negative 3 from the right side. Can't quite see that well, so let me fix that. So when we plug in 9 here, we'll have 3 minus 9 minus b squared to the power of 1/2. So what do we get now? We'll get 3 negative of 3 minus, plug in that, that'll give us 0. So we get -3, and this converges.